Okay, so today we're going to spend some time kind of taking what we have thought about in terms of the calculations and colligative properties and what we know about aqueous chemistry so far, and we're going to deepen them by kind of integrating and connecting that with your prior knowledge around intermolecular forces. So I want you to take a moment and think about how you would approach this question. So, how many water molecules are in one drop of water? You can think about that using the density of water. You can think about that using the volume of a drop of water. Um, you can make the argument that there's more than one size of a drop of water, so we might get a variety of responses here. But take a moment and on your own, think about how you would calculate the number of water molecules that are in one drop of water. And again, if you have some variation in your approach and responses, that's okay. We'll talk a little bit about how we approach this question. All right. So my estimate for this is that a single large drop of water could weigh about zero point 0.1 grams. And so my approach for thinking about this was to essentially say, if it's zero point 0.1 milliliters, then I know based on density, right? I've got 1 milliliter, 1 gram. So that's the same as saying I have 0.1 grams. I know the molar mass of my water, or I can calculate it from a periodic table. And then I know Avogadro's number. So in 1 mole, there are 6.022 times 10 to the 23rd. And that's molecules. Did anyone else approach this from a different avenue? Did you estimate the size of a drop of water differently, or did you have a different approach to the solution altogether?
In lab, usually about 20 drops is 1 milliliter of water. So
Yeah.
I went from there, which is about 0.05 milliliters per one drop. And then basically the same thing using
Nice.
density. Yeah.
That's perfect. And I feel like, I've been thinking about that. It's such a good point, Sid, because I feel like the aperture that generates the drop can really determine the size of that drop. So I feel like probably the best answer here would be some kind of a range. Um, so I really appreciate that. Now, interestingly enough, part of the reason why I thought this would be an excellent place to start our conversation is we've been talking a lot about freshwater and ocean water, but those volumes are also variable. So, for example, the Salinas River is famous because it's actually one of the longest rivers in the United States due to the multiple sources that contribute to it. So when I went to go and look and estimate, right, the number of water molecules in the Salinas River, Um, when the dam is full is one way to estimate that reservoir, but it's actually nigh impossible to know the full volume of the Salinas River because so much of the water that sources it are in aquifers below ground. And while there are some mechanisms to think about the size of those chambers and the volume of water in them, it's actually pretty tricky. If you were to take this as our kind of starting point of information and then use that, right, we could use Sid's estimation um, as a substitute as well. Whatever you think is the relationship between the size and the number of molecules. So for the Salinas River, the number that was reported for the reservoir was 22,320. And they did this as acre feet. So we're going to talk about different measures. Um, this is a common measure used for water, particularly for water that's associated with agriculture and irrigation. But we can actually convert the acre feet into liters, and that conversion is going to be a really useful one for you. So as you're thinking about your community water projects, this might be one unit that is helpful. But, in lab, you're used to thinking about volume in terms of liters, so that's why we're doing that conversion. So 1.233, and that's going to be times 10 to the sixth. And then, right, this is in liters, but because, right, we need to do a conversion to moles, we're going to use, again, our density. So I'm going to, for the sake of convenience, convert it to milliliters. And then 1 gram per 1 milliliter. And then our value here, 0.1 gram, 3.3 times 10 to the 21st. So for a drop of water, that's still a lot of molecules. But when I do this calculation, right, there are many more molecules, so I get 9.08, and that's times 10 to the 34. And again, that's molecules. So part of what I want us to be thinking about is, we have this tendency as chemists when we're thinking about these types of problems to think on a micro scale, right? To think about a single water molecule, right? But it's really important that we kind of go from this micro scale of, here's the Lewis structure of water to thinking about the aggregate or the colligative properties, say, for example, that are due to the number of water molecules, say, for example, in a body of water like the Salinas River. Um, Similarly, it's really important. Acre feet is not the only measure that's used. So, for example, Lake Tahoe has 36.15 cubic miles. So you can think about what that conversion would be. That's a great practice problem. And then if we think about the Pacific Ocean, right, this is estimated to be 660, and that's kilometers, so cubic kilometers. So, right, if we think about km cubed, right, you can also do that conversion thinking about, well, how do I take that and convert it to a volume that's usable? How can I take that usable volume and then convert that into a mass? How can I calculate, right, potentially the number of moles depending upon the size of that mass, and then, right, the number of molecules. So there are shortcuts we can make, such as an affiliation that says, well, this mass corresponds to this number of molecules, but you can also go through that full calculation process. And the reason why I want us to start thinking about this is that we've talked about colligative properties, we've talked about calculations associated with water, and what's really critical here is volume is going to have, right, specific intermolecular forces that are associated with that, and that's going to be really helpful as we start to think about, well, how do you, right, reconcile the behavior of water as an aggregate body? So what are ways you can think about the properties of individual water molecules and then the associations between those water molecules? So in order to get us there, we're going to do a little bit of practice with different forms of water. So I want you to take a moment and look at the table below. What do you notice and what do you wonder about the information in the table? This might require looking at a periodic table, but if we think about water and its composition as H2O and then H2S, let's just do a comparison between water and H2S. So water has a boiling point of 100 degrees Celsius. What about hydrogen sulfide? If you've ever experienced that acrid odor, sometimes associated with burning, um, hydrogen sulfide is gas and it has a terrible odor associated with it. Really interestingly, there's a significant difference, even though it's only one row in the periodic table, between water and hydrogen sulfide in terms of its behavior. You can think about hydrogen selenide and telluride, where they are on the periodic table, and what that means in terms of their behavior. So we're going to start to think about, well, how do you know when something is a solid versus a liquid versus a gas? What's some of the information that would help us discern what physical state a chemical would be in, and then what are some of the properties that are associated with that state? Any other insights for this table before we move on? Okay, something for you to think about. We'll come back to it. So when we think about boiling points, um, the hydride for tellurium, or H2Te, or hydrogen telluride, has a boiling point of -4 degrees Celsius. If we kind of move up in our periodic table, the next hydride would be H2Se, so that's hydrogen selenide. It has a boiling point of -42 degrees Celsius. And then, right, one more up, and that's H2S, the hydrogen sulfide. And that's water, right? So the boiling point, right, for water is really unique. It has an incredible boiling point compared to the other values, right? So -4, -42, -62, and 100 degrees Celsius. So what accounts for that difference? Well, if you think about a steam engine, we're going to do a thought experiment for a moment. When you heat water to make steam, there comes a point when you keep increasing, right, the heat that's being applied to the water, but the temperature doesn't actually change. And so the energy that you're pouring into the system um, seems to not have any change. But in fact, it's changing. We just can't always see it. So that energy goes in, it pushes the molecules in the liquid water apart, and it gives sufficient kinetic movement so that some of those particles can then escape and become gas. So in this process, the energy, right, that is within the steam or the gas is what we call latent heat. Latent means hidden. And a good way of thinking about that is that latent heat is like an incredible reserve of energy within the steam. And that energy then can be used to power, say, for example, an engine. That energy is also the reason why steam burns are so dangerous, because you are literally transferring the energy from the steam, say, for example, to skin. What's really interesting about this is that besides mercury, water has the highest surface tension for all liquids. So mercury is the only one that has a higher value that we know of. Um, and this really high surface tension, right, or its ability to form droplets or um, aggregates of water is due to the hydrogen bonding between water molecules. Now, we've talked before about how water has an exceptionally high heat of vaporization. And this vaporization is what's going to occur when you're transforming a liquid into a gas. And so, if you want to think about this, it's really an endothermic change, right? The heat of vaporization is 41 kilojoules per mole. And maybe most importantly here, it's not so much a reaction, is it really? This is a physical change or a state change. So I feel like this is a great example of we want to be, right, careful, right? When we're talking about physical state changes, it's not a reaction, right? It's a physical change or a change in state is the best way to describe this. So we want to use our language with precision, right? The transformation from liquid to a gas is a physical change or a change in state. And the reason why it's really important that we use that language with precision is because there are some energy changes that are associated only um, with physical change, and that's different um, than if, say, for example, we were talking about the energy change that's associated with a reaction. But endothermic means you're pouring heat in, you're adding heat in order to make a change. And then, interestingly enough, we also talked about vapor pressure. Well, our vapor pressure is inversely related to our intermolecular forces. So, the stronger the intermolecular forces, the lower the vapor pressure. Water has very strong intermolecular forces, which is why it has low vapor pressure. Um, and, right, it's even lower compared to larger molecules that have low vapor pressure. So it really is distinct and unique. Okay, the next piece that we're going to think about here um, is the viscosity of water. So um, you probably think of viscous liquids. Can you give me some examples? What are some examples of viscous liquids? Something that's thick or has a resistance to flow.
Like honey.
Oh, honey's a great one, right? I'm always super frustrated because the honey on my spoon, right? I have to exert a significant amount of energy to get the honey from the spoon into whatever I'm adding it to because of that resistance to flow. Molasses is a good example. Um, Sometimes you could think about um, lubricants, right? Have a low resistance to flow, they move easily. In fact, if you've ever felt that kind of slipperiness, sometimes associated with like liquid lotion, that again can be attributed to viscosity. Um, when we compare water to other types of liquids, we actually consider water to be quite viscous. So, because of the stronger intermolecular forces, water is going to be more viscous than liquids, say, for example, that only have van der Waals forces or liquids that have very weak interactions. And then we're going to talk a little bit about cohesion. So this is, again, a result of intermolecular forces between similar molecules. But the reason you can form a drop of water is cohesion. So water molecules, because of hydrogen bonding, due to the polarity of the water molecule itself, um, are the reason why they cohere. And if you've ever tried the experiment of can you fill a glass of water above the brim, you can fill it just barely above the brim without spilling, again, because of this property of cohesion. Cohesion is also the reason why you can essentially transport water molecules up systems like roots. Okay, so I want you to take a moment and in your notes, I want you to think about what you know about water molecules. And I want you to think about a claim, evidence, reasoning statement for why ice would be less dense than liquid water. Make sure that your evidence includes kind of the arrangement of the water molecules and how it might be different, say, for example, in liquid water versus ice versus gaseous water. So take a moment, think about why ice is less dense than liquid water. Okay, so ice is less dense than liquid water because what do we think is the reason for that? What's a good reason for why ice is less dense than water?
The water molecules expand to form the crystal structure of ice.
Thank you. That's brilliant. So the crystal structure of ice has a different arrangement of water molecules than liquid water. Ooh, except I can spell. Okay. So then let's think about, right, our evidence for this. So, right, one piece of evidence is that, right, ice floats on top of liquid water. Um, Another piece of evidence is as liquid water freezes, its arrangement or the distance between water molecules changes. You can physically see change. Any other evidence you can think of?
I think this would go with like the arrangement changes, but when water
Mhm.
freezes, doesn't it expand a little bit?
Yeah, it does. It's actually one of the reasons why if like you're putting something in the freezer, you don't want to fill it all the way to the brim. You want to give it space to expand. So when water freezes, it expands. Thank you, Sid. Okay. So let's think about then our reasoning here. So if we think about the reasoning, right? Why? Why is it that ice behaves that way? Let's take a moment and think about that. If we think about a physical explanation, right? So in ice, the water molecules, oh, we need an M, are held further apart. So if we think about like the increased spacing means there's greater volume of air. Compared to water molecules. And right, in terms of the actual arrangement, it's a tetrahedral lattice that creates pockets. Um, so, so a given volume of ice will weigh less than the same volume of water. So essentially, the way they take up space is different. Um, Interestingly, right, you can see this property in a variety of spaces, right? Like when you actually freeze ice, say for example, for beverages, but you can also see it in freshwater lakes, right? And the reason that there are hard surfaces on the top, but then there's still liquid below. So it's a really fascinating property that we associate with water. Okay, so the next piece then that we're gonna kind of wrangle in terms of our thinking, there are all these properties of water due to its intermolecular forces. We're gonna think about those properties in terms of something formally called a heating curve. So on our y-axis, we have temperature in degrees Celsius. On our x-axis, we have time. Sometimes textbooks will label this as the reaction coordinate, but because this is not a reaction, I don't want there to be confusion there, so we're just labeling the x-axis as time. So if we think about this, right, what does this figure show? What does a heating curve show us?
It kind of shows the boiling and melting point of something.
Yeah. Yeah, it'll show us the phase transitions. So really interesting, right? I feel like sometimes when we talk about this in, say, for example, a general chemistry context, right? It's usually taught as though that change is instantaneous, but the reality is it's not, right? So there's a period, right, where it's a mixture of ice and water, and a period where it's a mixture of liquid water and steam. And then I think the other piece that this shows really well is that, there are temperature ranges for a physical state. So from -20, right, according to this figure, to 0 is ice, right? From 0 all the way up to 100 is liquid water. And then from 100 all the way up to, say, for example, 140 is steam. Now, it's really important, I think, to note specifically for these heating curves that, right, the amount of hydrogen bonding, how easily those bonds form and break, changes based on the temperature. So the next piece then that we're going to think about is, well, how do you use heating curves? So we're going to think about the heat capacity of ice. So the amount of heat that's required to raise the temperature of ice, and that's going to be, right, always 1 gram by 1 degree Celsius. So there's a specific number associated with it, and it's always 1 gram per degree Celsius. That's what actually is, right, the change. And then we know that heat capacity is going to be unique for each substance, and it's really going to depend on the chemical nature of that substance. But really, right, the critical piece here for us is that when the temperature reaches 0 degrees Celsius, the melting point of ice, if you add more heat, it's not going to change the temperature because all of that ice has to melt before the temperature starts to change. So this phase transition temperature, all of the energy that's going in is what you could think of as potential energy, right? And we associate that energy with intermolecular forces, right? The hydrogen bonds that are forming or breaking, and that's going to really determine the state, right? The behavior of that chemical. So if we think about then the strength of an intermolecular force, right, we can also take that, say, for example, and think about the heat of fusion. So this is the heat that's required to melt a solid. So if you wanted to go from solid ice back to a liquid, or if you wanted to go, right, from a liquid to a gas, that would be the heat of vaporization. All of those are going to be determined by the forming and breaking of hydrogen bonds or the intermolecular forces. So if you have higher intermolecular forces, then you're going to have higher melting and boiling points. It's going to take more energy pouring into that system in order to be able to break the intermolecular forces. Now, most intermolecular forces are weaker than chemical bonds. So for example, if you think about the OH bond in water, right? So if I wanted to break this bond, in order to do so, I would have to put energy into my system. So if that was the bond I wanted to break, I would have to pour in 935 kilojoules per mole. If I wanted to break the bond in ice, right, the heat of fusion, that's only going to be 6.02 kilojoules per mole, right? And if I wanted to break the remaining intermolecular forces, right, in the vaporization of water, that's 40.7. So if you want to think about it, right, this is what we think of as the conventional covalent bond, right? That has a very high energy in order to break the bond. Intermolecular forces are weak by comparison, right? If we're thinking about an intermolecular force, that would say, for example, be the hydrogen bonding between the hydrogen of one water molecule and the oxygen lone pairs of another water molecule. So if I wanted to break that bond, it's going to be different for ice, say for example. So the ice to break would be 6.02 kilojoules per mole. Whereas if I was breaking it in liquid water, so it's hard to differentiate by color, but if instead of being ice, this was liquid water, and I were to think about the energy that I have to put in to break this bond, right, that would be 40.7. So this is ice, relatively little needed. If I'm going from ice to liquid where I'm breaking that bond, so that's 6.02. Whereas if I'm thinking about liquid water and I'm going from liquid to gas, that's going to take more energy. And the reason for that is because, right, I'm completely dissociating that water molecule from the rest of the liquid and it's escaping into the atmosphere. So, a really important takeaway point for us and something that we'll be grappling with this week, right? The strength of our intermolecular force then is going to depend on, right, the magnitude, right, of charges, right? All intermolecular forces are electrostatic in nature, so it's really coming down to partial positive, partial negative charges and how that affects the behavior of water. Okay, So we've thought about different phase changes with respect to a heating curve. The next piece that I want us to think about, and this is just a really important refresh your recollection, when you look at this chart, what's the difference between intermolecular forces and intramolecular forces in terms of the strength of the interactions? What's your big takeaway if you look at this figure?
Intramolecular forces are much stronger because the graph seems to be almost like exponential.
Yes, yes. Thank you. That is the key takeaway that I want us to see is, right, when we're talking about strong and very strong, we're talking about magnitudes of difference compared to weak or moderate. And even within intermolecular forces, they are not all the same. So London dispersion forces or van der Waals forces are much weaker, and those are, again, dependent upon distance, right? So if you have molecules that are dilute and far apart, those forces disappear almost altogether. Whereas hydrogen bonding is stronger, but it's not anywhere as strong, right, as, say, for example, an ion-ion or a covalent bond. That's a really important takeaway. Note, these are again in kilojoules per mole, giving you the relative scale. But as Sid said, it is, right, magnitudes of difference in terms of the strength of the intermolecular forces. Okay, so here's our big kind of wrestling moment. So why does water have a higher boiling point than something like HF or NH3? So this is where, right, we're leaving general chemistry behind and we're starting to think about more nuanced arguments um, in aqueous chemistry. So um, it'll be helpful for you to draw the Lewis structures for water, for HF, and for NH3. I want you to think about electronegativity in your argument. So it'll probably take me longer to draw these than it will you, but take a moment and think about, right, why does water have a higher BP or boiling point than HF, hydrogen fluoride, or ammonia? So to be able to answer this question, part of what we have to think about are the properties. So, right, if we think about, say, for example, water, right? Water, what does it mean to have a higher BP? Water has greater cohesion, right? More hydrogen bonding, right? That's really the reason. I can form more hydrogen bonds with water than I can with HF, right? And so if you want to think about that, it's because, right, where can I form a hydrogen bond? Well, I can form a hydrogen bond here at this hydrogen. Oh, let me change, do a different color. So this can form hydrogen bonds. 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 So if I wanted to max it out, right, the reason ice has a tetrahedral lattice arrangement, right, is because I can form four hydrogen bonds. So maybe up to four is a good way of describing it. Doesn't mean you always form four, but it has the capacity to form four hydrogen bonds. So by comparison, if I'm thinking about HF, how many bonds, hydrogen bonds, can HF form? This can form four. What do we think about HF? And here we can talk about hydrogen bond donors and hydrogen bond acceptors, right? So, right, the hydrogen has the partial positive, so we can label that. Oxygen has the partial negative. So if we think about this, right, that's one of the distinctions. Are there any other distinctions that we think are relevant? Oops, sorry. As to why water has a higher BP than HF or NH3? We can think about the electronegativity differences. That's going to be a key distinction here. So because of how electronegative fluorine is, it holds on to that hydrogen very tightly. In fact, HF is considered a weak acid because it doesn't want to let go of the hydrogen due to the electronegativity of the fluoride. So each of these molecules, it should be clear, do, right, experience hydrogen bonding. Right? What's the difference though in their behavior? Most folks would make this argument based on polarity, right? But that really fundamentally comes down to electronegativity. So ammonia, right, with its three hydrogen bonds, has stronger intermolecular forces, right, than say, for example, HF. But it also has a different shape. This shape is bent because the two lone pairs push each other away, whereas this shape, right, is different in terms of, right, its structure. So while they're technically tetrahedral because of the arrangement of the electrons, their actual molecular geometry is different. And so if you think about the number of possible interactions, that's going to start to change the way that these molecules behave with each other. Okay. So if we think about then gas, right? So ammonia is a gas, water can be a gas, right, at the right temperature, right? As water boils, right, its hydrogen bonds are broken. And the reason for that is the kinetic energy or the temperature change the heat, say for example from the stove, if you have a pot of water on the stove, that heat gets imbued into the steam particles and then they start to move fast and they move far apart. And they move so far apart that there isn't time for hydrogen bonds to form. And so as you reach the critical point above steam, fewer and fewer hydrogen bonds occur, and that's going to fundamentally change the behavior of these molecules. So we referenced this earlier, right? The lack of hydrogen bonds explains why, say, for example, hot water is so different than a steam burn. So steam contains all of the energy that you used to break the hydrogen bonds in water. So if steam, say, for example, hits your face when you take the lid off the pot or when you're pouring out water, you have all of that energy and the heat gets released. And so it's a transfer of that energy then to your skin. So if we think about this, it's really important, I think, especially in terms of aqueous chemistry, to have a distinction between steam and water vapor, right? So what do we use to describe the white cloud of water droplets, say, for example, that are above a boiling kettle, right? What's the difference between steam and water vapor? Take a moment and see if you can come up with the difference in your own words. What do we think? What's some of our thinking on the differences here? I'll see if I can record our thoughts. So water vapor is a generic term for all gaseous H2O, regardless of temperature, and right, regardless of whether it's visible or invisible. So, for example, there's plenty of water vapor that's in the air. You may not ever see it. Steam, however, right, refers to the visible water vapor, often due to the condensation of water droplets. And right, um, usually it's associated with boiling water. So this is a really great example where academic language can help us out, but it's really interesting because conventionally these terms are often used interchangeably, even though, right, there are subtle distinctions between them. And, right, the context really matters. So if you're talking about the water vapor content in air, right, that might be different, say, for example, than the amount of steam above a boiling pot. Okay. Last but not least, we can think about this in terms of differences in temperature, right? It's not wrong to call gaseous water coming out of a kettle water vapor, but saying that it's steam tells us that it's in a vapor state and it's hot. So water that's hot is often what we refer to. So another way of saying that is all steam is water vapor, but not all water vapor is steam. Okay, so I want to pause here and switch to our Canvas page just because I have two pieces of information that I want to make sure to share with you all. Okay, so we're going to do an example on Thursday of, oops, sorry about that, of the overview case study. So each of you has selected a water site. I'm going to choose one of the ones that has not been selected, and I'm going to walk us through how to do the oral component of the claim evidence reasoning as the overview. Um, and then I will post an example of what the state of water, the 2 to 3 page summary looks like. So you'll have a chance to see both of those examples on Thursday. Next week, we're going to look at data wrangling, so some of the calculations, figures, and analysis that are associated. Um, and then we'll have some examples of some solutions for you. All of this is posted on Canvas, so if you're like, hey, I need a quick overview, you can always refer back to this to get a sense of the types of questions that you're going to be answering and the examples. And then I do have specific for us the references. The other piece that I think is really important um, for us to take a look at, and you can see this in Canvas, is I have a Steam Notes PDF that actually kind of walks through a little bit more specificity for what we talked about today. So if you need a quick refresher on units, an explanation of the STEAM statement, and then some calculations here. Um, we'll look at some examples of that. So this is the Clausius-Clapeyron equation, and it really talks about, right, how we can calculate that latent heat. So we'll have some practice problems that we're going to take a look at on Thursday for that. But that's a reference for you in terms of what we started talking about today. So what are we working on this week? So we have a pattern of inquiry that looks at precipitation. We're going to use that and the content that we're covering on Thursday to help make sense of some of these calculations. You've got a reading quiz that I think is a really important component for you to start organizing the information that we've talked about in class. So we're about halfway through. It's going to be super useful for you to start thinking about how to build out your concept map. If you recall, when we did the very first day of class, one of the things I asked you to do was to share what you already know about water. So that's a great place to start. I'd like you to take that and build additional connections based on what we've covered in class so far. And then the last piece is I've got a heating curve graph that is a great way to kind of walk through what we talked about today. Think about the analysis of the graph and then which parts of the curve do what. So this is a really great kind of mental exercise to help make sure that you are making sense of the heating graph. I would incorporate something like this into your concept map, kind of as you're building out that knowledge. So all of those are resources that are intended for you to kind of answer your reading quiz, which is building a concept map. So there's some resources here for that to kind of help stretch and expand the knowledge that you already have. And then I will see you all on Thursday. We're going to talk in greater depth about precipitation. So if you'd like, you can get started on your pattern of inquiry. I just want to give a quick overview for what that looks like. So on Thursday, we're going to be talking about dew point, and we're going to use, right, all of the conversions that you already know of for Fahrenheit, Celsius, Kelvin, as well as the pressure unit, so atmospheres, millimeters mercury, PSI, right? Make sure that you're in a comfortable space in terms of converting between units, because that's definitely work that we'll be doing on Thursday. And for those calculations, we're going to operate under the assumption that those conversions are something you're comfortable with. If that's not the case, please shoot me an email. I'm happy to go over any of these conversions with you in office hours. And then we're going to use a nomograph. So we're going to calculate the boiling point for water at various pressures. That's a super useful tool for anything from distillation, right, to certain industrial processes. And then I want you to go through the thinking to make sense of physical and chemical changes, but really to think about them in terms of, if it's a physical change, what intermolecular forces are in play. If it's a chemical change, what bonds are breaking or forming. So start to kind of go beyond just the physical or chemical and start to think about, well, what's physically changing about the relationship between the molecules, right? Or what types of reactions are occurring. Is it acid-base? Is it synthesis? Is it degradation? And then we're going to kind of dive deeper. And on Thursday, we're going to look at the calculations associated with, well, what actually makes up weather? So when you have wind, right, and you have temperature change, how does that impact dew point? So that's what we're going to be working on Thursday. And then we're going to use that to actually think about, well, why do we form clouds? Why do clouds take the shapes that they have? Why is it that those cloud shapes change? How can you use the clouds to be able to predict the type of weather that's going to occur? And then what is actually the chemistry that's occurring, right, as those clouds change? So more coming on Thursday. If you've got questions, please don't hesitate to reach out. If you haven't done so, please make sure to sign up for your community water project. And then I will make sure to touch base with you once I post the examples for you to check out. So thanks so much for a great day. I hope you have an awesome rest of your Tuesday, and we'll see you soon.